Okay, so today's concept is solution concentrations. In chemistry, the word concentrate means something different than like everyday life. Like in everyday life, if I ask you about concentration or concentrating, that usually means like you're thinking really hard about something, right? But that's clearly not a chemistry term. So, you guys ever buy like orange juice that's like that frozen stuff in the can? We call it from concentrate. That's the other way we'd use the word concentrate. Um, Basically, it means like there's so many different synonyms you could use. You could say that it's really strong or it's really thick, right? But at its core, concentrate basically means that there's a lot of solute in the solvent. You guys remember that those terms from yesterday? Solvent is like the I don't know. I just made my water bottle here. This is a good example, right? The solvent is the water. The solute is the stuff that I'm going to dissolve in it, right? Well, a really concentrate solution would be if I didn't just pour one of my packets in there, but I poured like 3 or 4 of them in there, right? Then it's really concentrated. Fair enough? So, which I want to start there with this picture. I know yours are not in colored the same way, but this is a good idea of a spectrum here. This is dilute. This is concentrated. Basically, it's how much more stuff you shove inside, making it thicker or stronger, right? My wife's grandparents, there's always a running joke in our family around Thanksgiving because when they make juice for Thanksgiving, that one of them always makes like the weakest juice imaginable. Like it's like, oh, it's barely flavored water, right? And then the other one, they just keep dumping more and more, and it's like thickest juice ever. You know what I'm saying there? So the words I want you to know then are dilute and concentrate. Those are the official terminologies we should use. So um, a lot of people will try to use the words weak and strong when it comes to this, but in chemistry, weak and strong actually refer to something different, which we're not going to cover in this particular section of the course. But I want to make sure I teach you the right terminology because I think you actually use it in Science 30 if you guys ever take Science 30. So don't use the word strong to refer to concentrated. Strong actually refers to something else. Fair enough? So our goal today then is to put a numerical value to how concentrated something is. Because obviously this guy right here isn't very concentrated, but this guy here is. We need a way to like quantify that. So I'm going to show you guys 3 different methods of how to quantify just how strong it is. The first one for concentration is known as moles per liter. It's often given a capital M as its unit. It's known as a molarity. I'll even write that out for you here. The units would be known as a molarity. And pretty much everything in the chemistry lab is measured in terms of molarity. Maybe another day I'll go and I'll grab you some of the beakers that are back there. But when I purchase stuff, I purchase it with this as the units that are involved. It's not really used in like everyday life stuff like cleaning solutions or things along those lines. So here's the formula. Actually, I have a data book here. I want to see what they have for formulas in here because you might want to write this down otherwise. Give you a formula on this? No, they don't, do they? Well, they do too. Here we go. Can you guys find page 10? Page 10, it's like way the heck to the back. It says stoichiometry and solution formulas. The one that you're going to be looking for is the second one down. It's capital C equals N over V. It's not what I have written here, but essentially if you want to find a concentration, concentration is usually done in capital C. It's the number of moles of solute divided by the volume of solution. So I need to do a quick review before we move on. Do you guys remember what a mole is from Science 10? Okay, that's fine. You know how when you go to the store and you want to purchase stuff, sometimes you probably buy things one at a time. Like for example, if I want to go buy a jar of tomato sauce, I buy them by the jar. But there are certain things where it wouldn't make sense to buy them one at a time because you're buying so many of them. For example, if I go down the bulk food aisle, I don't like say I buy chocolate chips in bulk. I don't buy one chocolate chip at a time, right? That's kind of ridiculous. They make you pay based on weight. Does that make sense? Or other examples is maybe they make you pay based on how many of them you have. So if I go down the fruit and produce aisle and I want to buy apricots, maybe I can buy like a big case of apricots and I get 12 of them. Does that make sense? And sometimes we don't buy them individually. We buy them either based on mass or based on how many there are. Okay, now back to chemistry. A mole is a way in which we try to standardize a large number of things, because really we should talk about atoms one at a time in chemistry. But I mean, if you look at my water bottle here, there's clearly more than one atom in there, right? There's like a lot of atoms. So a mole, if you want to maybe just write this off to the side, 1 mole is 6.022 times 10 to the 23 atoms. It's kind of like a dozen. You know how like when you buy things in a quote-unquote dozen? If I buy a dozen eggs, I'm actually buying 12 eggs. Well, whenever we talk about a mole of a substance, we're just talking about a whole lot of atoms. Rather than counting them one at a time, we count them that number at a time. Does that make sense? So in a long convoluted way, if you're going to calculate concentration, I'm really asking you how many atoms you have in your solution. But since we can't count atoms one at a time, because you're going to have billions of them, we count them moles at a time. So let's do an example. You had learned this last year. We'll kind of build our way up, I guess. So here's our first one here. What is the concentration of a solution if 5.6 moles of sodium chloride, that's basically salt, are dissolved in 20.8 liters of water? I know this isn't the question here, but how many atoms are we dissolving? Well, 5.6 times that number, that's how many atoms we're dissolving. But like, who counts them one at a time? By atoms, right? So it makes more sense to count them in terms of like a larger grouping, like a dozen. So for this one here, why don't we use the formula on your sheet? The formula is C equals N over V. That's the formula we're using. So to find our concentration, we just need to know how many moles we have. So our moles was 5.6 moles. And then our volume was 20.8 liters. It's basically just like we did in physics, right? Just plug in the two numbers and divide them from each other. So if you have a calculator nearby, just divide those two values. Let me know if you don't get this number here. I'll start writing it out. 0.26923, etc. You guys able to get that value? Okay. So this is a measure, a quantitative measure of how concentrate a solution is. And so if I give you a solution of a concentration of 0.2 and a solution with a concentration of 0.7, which one is stronger? 1.7. Does that make sense? Okay, a couple other things I need to remind you guys about. Have you heard about sig digs before? Significant digits? This number right here, we can't write out all those digits for forever. That's ridiculous. So we need to round at some point. So the rules are whoever has the least number of digits, that's what you have to round your final answer to. This 5.6 has 2 digits. The 20.8 has 3 digits. So 2 has less. So this final number right here can only have 2 digits. But one of the rules of sig digs is that this 0 in front doesn't really count as a digit. Like 007, like James Bond 007, it's really just 7. Right? Like zeros in front of a number don't really count. You can keep writing zeros in front for all you care. So the final answer here is going to be 0.27 moles per liter. See how the 2 counts. The 6 is the last number we'd have, but the 9 would round it up from a 6 to a 7. So this has 2 digits. Another way you could write this, though, is you could write it as 0.27 capital M. Capital M means molarity. It's just a measure of how strong something is. Well, I don't want to use the word strong. It's not the right word. It's a measure of how concentrated something is. Okay, one example in. So far, so good? Okay, you might have noticed our notes are basically just a crapload of examples. There's not a lot more to it than examples. Okay, let's try this one here. What if I were to not measure things particles at a time? Remember how I mentioned like when you go to the grocery store, you could buy like 1 can of tomato sauce, but you can also buy things based on a weight, or you could buy things based on a number of how many you have. Well, if you buy 10 stalks of lettuce, it costs per stalk. So, I don't know. Right? Well, this is a bit of a different one here. Now what we're doing is we're not we're not buying based on how many you have, we're buying based on weight. Right? Can you guys see how it's 24.6 grams of something? So if we want to use the formula that I just showed you, which is that your concentration is the number of moles divided by the volume, we have the volume. The volume's pretty easy. You've got 4.00 liters. That one's ready to go. But right here, we need to have a mole amount. We need to know how many we have, not how much they weigh. I'm just going to write this out here. You don't have to write it out if you don't want, but you could. N is a measure of like how many you have, but we often use M as how much it weighs. N is moles, and M is mass. It's kind of unfortunate that they really both start with M, like moles starts with M, mass starts with M. So the scientific convention is N is actually how many moles something is. So that's how many there are. Mass is how much it weighs. What'd you do?
We both knew how much it weighs, but we spelled it like W-A-Y-S. So I was laughing and I showed the number sheet the same thing.
There it is. Okay, so what we need to do is find a way to convert between how much something weighs and how many of them there are, because this is what we're looking for. We need to find that mass right there, or this moles right here. So it actually so happens that there's a formula on your sheet right above the one that we just used that looks like this. N equals M over capital M. Can you guys see that formula? With my students in chemistry, I actually hesitate to use this formula. I really dislike it because I find that kids usually get confused about what N and M and capital M stand for. So I'll show you how to use this formula if you like it, but then I'll show you what I would have taught you last year in grade 10, and you guys can choose which one you like better. We need to solve for N right here. The good news is, though, we know mass, don't we? Because it told me a mass. It said its mass was 24.6. So all I need to do to find N is just divide by capital M. And if you read on the sheet here, capital N is a molar mass. Do you remember how to find a molar mass off of your periodic table from last year? Yeah, do you remember how to calculate a molar mass using your data book? Yeah, add those numbers up, right? So see how we're working with sodium hydroxide right here? Just put it up in the corner here. You need to just add up how much they weigh. Go back to my grocery example. Let's say that you wanted to make your own nuts and bolts mix. So you went to the went to the bulk aisle and you wanted to purchase some pistachios. Well, pistachios have their own price and weight. And then you wanted to add some peanuts. Well, peanuts have their own price and weight. Right? It's the same sort of thing here. Sodium. Well, sodium weighs, can you guys find this number? It's 22.99. Let's find that value on your periodic table here. So, in a way, if you like to think of the grocery store example, that's like how much pistachios cost. They cost $22.99 a gram. Only in this example here, that's really like, that's how much it costs for a mole of them. So if you were to buy, this number that we wrote down way back here, this number right here, if you were to buy this many atoms, that's how heavy they are. So sodium atoms are 22.99 heavy. But you don't just want sodium atoms, you want oxygen atoms. How heavy are oxygen atoms? Right on the dot. Right? So similar to my bulk food example, everything has a different sort of weight to it, right? Like some foods are very light, some foods are very heavy. Well, same thing with sodium and oxygen. Sodium is heavier than oxygen. How does that compare to hydrogen? Very light. Hydrogen is like the lightest thing we have, 1.01. Grand total then, if you add them all up, is actually 40 right on the dot. So what this number here is this is known as a molar mass, and this is how many grams you have in a mole. So if you were to have 1 mole of atoms, which is like that 6.02 times 10 to the 23, if you were to have that many atoms, it would weigh 40 grams. Well, that number goes down here for this capital M then. 40.00 grams per mole goes down there. Mathematically, what ends up happening is these gram signs cancel, and you just have to divide them by each other. So you got to take 24.6 and divide by 40. And I got 0.615. That's how many moles you end up with. let me see that I can make sure this is clear. You went to the scale at the store. And at the store, you weighed out 24.6 grams of the food you were going to buy. Okay? This right here is how much like one collection of atoms equals this many grams. So long story is we've now figured out how many atoms we have. This, I know it doesn't seem like this is an atoms number, but 0.615 is like, well, a portion of this number right here. Think of it like a dozen. We didn't buy one egg or two eggs. We bought like 0.6 of a dozen. Go follow that? Long story short, this number now here is the number that needs to go up there. Because that's how many moles we had per liter. So for our last step, I should now take 0.615 and divide by 4 liters. So divide that by 4, and I get this value here. 0.15375. Get that number, 0.15375. Okay, but we got to round that number. How many digits am I allowed to keep? 3. Because 24.6 is 3 digits. 4.00 has 3 digits. Zeros on that side count. So we need 3 digits. Now, this 0 here doesn't count, but the 1 does, the 5 does, and then the 3 we have to figure out whether to round the 3 up or not. Yeah, so that's the final answer. 0.154, and then I'll use capital M. This is our final answer. Sorry that it's kind of in the middle of the page. That was our final answer. Okay, let's compare it to the previous one here. This is 0.154 concentrated. This last one here is 0.27 concentrated. I now have a way of ranking them. This one is a stronger solution. It's not the right word, but like this one is grandma's juice, and this one right here is grandpa's juice. Grandpa was pretty weak. He's pretty stingy, and this one right here is obviously there's more to it. Does that make sense? Okay. I didn't show you this method last year of using formulas because my personal opinion is that kids get confused because there's C and N and V and N and M and capital M. So let me show you what I did last year, and then you guys can choose which one you like better. Last year I would have shown you this. I would have said take 24.6 grams, and I would have written it out twice, and I would have asked you which way looks correct. And I would have said, let's times by 40 grams in a mole, or let's flip it and make a mole over 40 grams. Does this ring a bell at all? And I would have asked you which one of these two methods would like cancel the grams properly. Does the top one cancel the grams out, or the bottom one cancel the grams? You guys can see it's the bottom one, right? Because this grams here cancels with that one here, so the top one's no good. Well, honestly, that's exactly like what we did, because 24.6 divides by 40. Well, right here, I did the exact same thing. 24.6 dividing by 40, it would have given you the same number. It would have given you 0.615 moles. I find this one better because I think kids can visualize what's happening more. Whereas on this top one right here, kids just plug numbers into formulas and they just hope to get the right answer. So I don't care which one you pick, but this number here is now your moles number, N. You then have to divide it by your volume number, which was 0.4. No, it's 4.0. And that's how we got our answer. So either way, you kind of get to the same spot. So the difference here, though, compared to the last one, here we just literally took moles and liters and divided by each other. Here we had to link it. It gave me a weight. I don't want a weight. I want a numerical quantity of how many there are. Once I know how many there are, then I can divide. Does that make sense? So, grocery store analogy one more time. We can measure things individually, like buying one can of something, but that never works in chemistry. We could buy them in groupings of something, so you could pay for like a dozen eggs, or you could pay based on weight. This is a weight number. This is a numerical number of how many there happen to be. It seems weird because it's not a whole number increment, but it's like, this is like dozens. Divide the two, you got your answer. Sound let's try another example. This one kind of works backwards. Chemical analysis requires that you have 2 liters to make a 1.15 mole per liter solution. Our goal is to figure out, well, how much mass do you need to get there? So let me use my water bottle as an example. It's actually convenient that I made this and it didn't dissolve whatsoever. I'm going to use the shaker. Let's say that I want to have a 0.150 moles per liter solution. Like, I want my solution to be that amount of concentrated. Okay? And I know how much water I'm going to put in, because my water bottle is 2 liters. Pretend this is a 2-liter water bottle. The question then is, well, how much of the powder should I be pouring in? Should I be pouring in 5 grams, 10 grams, 100 grams? Does that make sense? So we're kind of reverse engineering this. Rather than me telling you the mass and me telling you the volume, I'm going to tell you the volume. I'm going to tell you what concentration you want to end up at, and I want to say, well, how much mass should you put in? So here's how I show my students in Chem 20 how to do this. But we can use formulas in another example in a bit. I would start off with the 2.00 liters. And then I'm going to write out 2 possibilities here. You guys can tell me which one you think is correct. I'm going to either times by 0.150 moles per liter, or I'm going to times by a liter for every 1.50 moles. Which one of these looks like a better way of starting this off, top one or bottom one? You say top. You said bottom. Why do you think the bottom? Because you see how the liters number here would cancel? That would be useful to us, right? So rather than, by the way, every time you have like a fraction value, you can flip it upside down if that's useful to you. But I think in this example here, hopefully you'd see that flipping that fraction upside down here was not helpful. So now we're at moles. See how moles is the unit that's left? Well, a moles is a how much, like a number of particles. But I don't want the number of particles, I want to know how much they weigh. So what I'm going to do is I'm going to multiply, and I won't write it out 2 different ways here, but I'm going to write out grams over moles. Because can you guys see how the moles would cancel them? Now I could try doing grams and moles and flip it upside down, but hopefully you kind of get the idea of like, if I put it in this orientation, it cancels. The only thing I'm lacking then is, well, what is my grams to moles ratio? How heavy is this particular molecule? Am I buying pistachios or peanuts? Like, what's the weight ratio? Well, that's what I get from right here, AgNO3. That tells you how heavy it is. So I'm going to go look up the mass of silver. So, periodic table. Silver weighs 107.87. You guys find what that value is on the table? Okay. But you're not just buying silver, you're also buying silver mixed with a nitrogen. So nitrogen adds a little more weight, 1401. And then you're also buying some oxygen. Now oxygen on its own weighs 16 right on the dot, but you need 3 of them, yeah. So the way I usually would have written it is I would times by 3 right here, and then I put a line underneath and just add it all up, but don't forget to times the 16 by 3. So what we're really calculating here is how heavy is this particular molecule. Because just like at the grocery store, pistachios weigh more or less than peanuts, weigh more or less than walnuts do, right? So everything has its own weight to it. I got 169.88. I see on Facebook that your mom sells that, or as part of that, same thing that Fonda and Miss Gregory are doing with that Valencia stuff. Does that work good? That's what this is. I'm just trying it for the first time. They make a lot of money with that? I always see Mrs. Gregory's posts on Facebook. It always seems like she posts about it all the time. So I see your mom in some of her photos sometimes. Anyways. Yeah? Track. All right, anyways, this value right here then is the grams per mole number that we were looking for. So should we put the 169.88 with the grams number or with the moles number? With the grams number, yeah, because that's how heavy it is. It weighs 169.88 grams to have that many atoms of substance. So the last thing we got to do then is just multiply these by each other. Take 2 times by 0.150 times by 169.88, and that'll tell you how many grams of solid you should put into your container. So 2 times by 150 times by 169.88, and it gives you 50.964. Okay, one last thing here. We can't keep that many digits, though. I only get to keep the lowest number of digits that my original values had. So 2.00 has 3. 0.150 actually has 3 as well. So we need 3, which means we get to keep the 5. We get to keep the 0. And then what we're not really sure about is what happens to that 9. Should the 9 round up or go down? Because the 6 is more than halfway there, this actually shouldn't be a 9, it should be a 10. So the way we write the 10 is 10, like that. You see like how the 10 is right there? You should add 51 grams. How am I doing so far? You guys able to follow this? Okay, that's good. Let me show you one more way of solving this. Let me use the formulas on your formula sheet as well. Now, I think this is the easiest way of doing it. That's my personal opinion. But I want to give you options. So here's an alternate way of doing it. The formula that we started with was C equals N over V. Okay? And we were actually given a concentration and a volume, because the concentration would have been, what was it again, 0.150? Yeah. 0.150 moles per liter. And then we also knew the volume was 2.00 liters. So you could just use the formula. So mathematically, how do you get N by itself? Well, see this 2 that's in the bottom of the fraction? Times it to the other side. So really, you got to times it to the other side. So imagine that 0.150 has to times by 2. That gets you N. Which means that it's 0.300 is N, because 150 times by 2 is 3. Well, then you could use the other formula, the one written above it, which is that N equals little m over capital M. And actually we have these values too, because little n is 0.300, because we just found it. Little m is the mass we're looking for, and then capital M is that molar mass. But we already did that. That was 169.88. So then, same issue as last time. How do you get this little m by itself? Well, you times the 169.88 by that number there. At the end of the day, really what happened is this number got times by this number to get that one, and then this number got times by this number to get the one we're looking for. I don't like this one myself, because N, M, little m, C, and V gets really confusing to me. But I mean, it gets you the same thing at the end of the day. If you took this 0.300 and times by 169.88, it should still give you that like 51 number as well. So like, they both kind of work. What do you guys think? Which of these two methods I showed you do you think is like the simpler of the two? Do you like the formulas, or do you just like kind of like writing it out and canceling stuff? Okay, that's my personal preference too. I think that as I show you more examples, that you'll probably like that. So let me try this one here then. You've got a sample of laboratory ammonia solution, and I'm going to give you its concentration. 14.8 moles per liter. Side note here. You know, the concentrations we used to be working with were like 0.2, 0.1. 14.8 is strong stuff. Like this would be the kind of stuff where it's like going to eat a hole through your flesh if necessary, right? Like this is strong, scary stuff, right? So my question then is, well, what's the chemical amount in a 2.5 liter bottle? Okay, now let me show you, again, two options. Option one, we'll use that formula. C equals N over V. 14.8 is my concentration. My volume is 2.5. Just swing that guy up there and you get N by itself. Chemical amount, is what we're looking for. Like chemical amount is how many atoms are in there. Like what's the molar amount. I prefer this though. I visualize this better. If I were to take 2.5 liters and I just multiplied by 14.8 moles over a liter, can you guys visualize how those liters kind of cancel? It gives you moles. So like my personal preference is just skip the formula entirely. But like it's the same work, right? In the formula, 14.8 has to swing up and times by 2.5. In this method right here, this liters cancels this liters, and you just have to times 2.5 by 14.8. I got 37. So like for a little context, this would mean like that you're buying 37 of that grouping of atoms, right? So it's like buying 37 dozen eggs or buying 37 dozen donuts. You're just buying 37 groups of a lot of atoms. Still good? Wait, let's talk about another method. Another way that we can measure concentrations, which again is how much stuff is inside your solution, is known as a parts per million. Parts per million is like we measure like say water quantity in parts per million, like something that's very, very small, very minute we measure. Any of you guys have like a well? You have a well? You ever get like testing done on it to make sure the water is like suitable for drinking? Okay. Like sometimes you might have like an inspector come just to make sure that it's still safe. Oh, and like there might be like a requirement that says that you can't have more than like 3 parts per million of iron or 2 parts per million of sodium, because if it's more than that, then it's like maybe unsafe. So parts per million is basically a very, very small amount. So the formula that I give my chemistry students is this: it's 1 milligram per liter. But it actually has a different formula on your sheet down here. Can you guys see at the very, very bottom there? It gives a formula of mass of solute divided by mass of solution times by 10 to the 6. Both of these formulas kind of work. It just depends on your scenario. Milligrams per liter is one way of making it work. The reason why is that in 1 liter, there is 1 million milligrams. That's the reason why this formula works that I have right here. You guys see that 10 to the 6 in this formula right here? 10 to the 6 is a million, by the way. Like 10 times 10 times 10 6 times is a million. So either one of these formulas should work for us. So let's do an example. What's the mass of chlorine present in 5 liters of solution if you have 6 parts per million? So 6 parts per million is very, very small. Like there's not a lot of chlorine in there. Right? But clearly there's some. So here's how I would solve this one. I'd say, well, let's start with 5 liters. 6 parts per million, though, can be written a different way. 6 parts per million could be written as this. This is how many milligrams there are in a liter. That's an alternative way of writing your units out. So let me show you 2 ways of doing this. You could do 6 milligrams per liter, or if you want to, since it's a fraction, you could flip it and do this one here. But you're already giving me a funny look, because like the first one's totally logical. The second one doesn't even look right. So take 5 liters times by 6 milligrams in a liter. You probably can do this one in your head. 5 times 6 is 30. So that means if you were to drink 5 liters of water, you actually ingested 30 milligrams of chlorine. A lot of times when it comes to this parts per million stuff, it's not dangerous unless you consume large quantities of it. Like for example, we often put fluorine into our drinking water to help with teeth enamel. If you were to drink like a lake of it, that'd be way too much fluorine, you'd get sick. But usually you drink a water bottle at a time. If I drink 1 water bottle, I'm getting like 0.00001 grams of it, right? But if you were to drink the whole thing, well, then you're getting lots of. Then it would be lethal. But you'd probably die because you can't drink that much water anyways. So, did that make sense at all? Let's try another one. You buy a bottle of sparkling water, and it says that there are 440 parts per million in there. What mass of minerals is present if you drink just 1 glass of water? So 200 milliliters. Now, the reason I throw this one in here is that it really starts sort of the same way. I would start with the 200 milliliters value. Remember how a part per million was a milligram in a liter? Well, if I were to times by 440 milligrams in a liter, yeah, see the problem here is that this is milliliters and that's liters. So I kind of have a problem. We're going to convert it, and often kids convert first, but you can actually convert afterwards if you want. I really don't want to have milliliters be up on the top. I want to have liters be on the top. And I really don't want liters to be on the bottom. I want milliliters to be on the bottom. Because watch this. If I write liters over milliliters, see how this milliliters cancels with that milliliters now? And this liters cancels with that liters now? I just need someone to tell me how many milliliters are in a liter. Correct, yeah. In 1 liter, there's 1,000 milliliters. There, we did our converting. Good job. So, on your calculator, take 200 times by 440 and divide by 1,000. Now, you don't have to do it in that order. You could divide by the 1,000 first and then times later, but it's the same work. So, I got 80. Is it 82? I didn't use 440, I used 400. You're probably right. Divide times by 440, divide by 1,000. 88, you're right, my bad. Good catch. That's a 440. Okay, so if you drink 1 glass of water, it means that you're getting 88 milligrams of dissolved stuff. 88 milligrams isn't that much, so. Still doing okay? Oh wait, there's a third way that we typically can measure concentration. This one is often found on foods and stuff in the kitchen. For example, when you buy, like, say, cooking oils or vinegars, they often give you them as percentages. If you were to go to Blair's Kitchen and get, like, I don't know, malt vinegar, it might say on the bottom. Next time you're there, by the way, take a look and see if you can find like a little percentage on the bottom, like say 5% W over V or 5% V over V or 3%. That really tells you how strong the vinegar or the oil is that you're cooking with. I might even have some in the back of the lab. I didn't have vinegar like in the kitchen, but I have some hydrogen peroxide. Just your basic stuff that you'd buy at the store. Well, not this one. You can't buy that one at the store. Can you guys see how on the bottle here, this one says it's 3% W over V? That's a measure of how concentrated it is. This is 3% concentrate. And you can just buy this at any Shoppers Drug Mart, right? Well, that's the one that we used. We actually used this one in one of the labs that I did before we left on our break. This guy right here, if you can see, it's 30% solution. So, I mean, logic would dictate that this one to this one is 10 times more concentrate, which is why it's in a smaller container, right? Because if this one is 10 times stronger than this one is, you need 10 times less of it, right? To do the same amount, right? It's like when you make orange juice, right? Because you buy it in that like frozen concentrate pack, you only need to have a small amount of it as opposed to having a whole bunch of it because it's really concentrated. So, anyways, that's what this one is used for. There's 2 different conventions. One of them is volume divided by volume times by 100. The other one is weight divided by volume times by 100. And you get one of these ones in your formula booklet. You guys get the volume over volume times 100 formula. But I might give you some weight over volume ones as well.
How come it says to keep in a dark, like cool, dark place? It's already in a dark bottle.
Well, probably because it has the ability to oxidize with light. So, but you're right. That's probably why it's also in a dark bottle too.
So I was just gonna say, because that one's in a clear bottle.
Yeah. Probably the assumption is that this one here is going to be stored in the chemical lab because that's where it should be because of some of the oxidizing and corrosive properties of it. So,
So don't
Oh, yeah.
use that one.
well,
to
like,
clean your
have you ever
cuts?
used hydrogen peroxide to like clean a cut, or like we use it to dye hair and stuff like that? Like it will burn. So.
So don't use the little one to clean a cut.
No, because it's way too concentrated, right? Like you would want like 2 drops of it. All right, let's give this a try here. I've got a few more examples I got to get through. I've got 10 milliliters of acetic acid, and we dilute it to a total volume of 200 milliliters. Let's find the percent by volume. You guys are going to like these ones here. These ones are actually really drop dead easy, because your formula was to find a percentage volume over volume, you take the volume of the solute, you divide by the volume of the solvent, and you times by 100. Oh no, not solvent, solution. Solution. Yeah, that's really it, right? It's like 10 out of 200 times by 100. This one most kids like because it's like how you calculate your grades in school, right? You just got 10 out of 200 on the test. Well, okay.
Good job.
But that's actually, we probably don't want it to be super, super high in terms of chemistry because the more concentrated it is, the more dangerous it might be. So, 2%? No? Oh, 5%. 5%. You guys get 5%? It's actually not 5 though. You gotta watch your digits again. See how this had 3 digits afterwards, and this had 3 digits? Yeah, you actually have to make it 5.00 to do it properly. You have to add some more digits afterwards. Well, you'd have to add it to get the right number of digits, because this has 3 digits, this has 3 digits, so this one just there only has, so, I mean, you can't do 5.000, that has too many digits then. So, that makes sense then? Most people like those ones are pretty straightforward. So. Boy, last thing I gotta talk about. When you make a solution, there's 2 main ways of making a solution. You already watched me make one today. I just took solid crystals and I poured them in the solution and I'll shake it up and then it's made, right? But there's another way you can make it, well, mostly shake it up. I'll have to stir them somehow better. But there's another way that you can make a solution known as dilution. And I'm fairly certain you guys are intuitive with this. If I have this 3% solution and I have this 30% solution, but I don't want it to be 30% solution, I just add some of this to water and I make it weaker. Does that make sense? Like when grandma makes her juice for Thanksgiving and it's, whoa, that's too strong, right? We'll just add a little more water and now it's nowhere near as concentrated. Does that make sense? And so that's this last formula I have to show you, which is the third one on the list there. See that CIVI equals CFVF? It's more or less the same formula that I have here, only rather than I's, I used 1's and 2's, they used I's and F's, but like same concept, right? Initial and final, or before and after. So, I pulled this out of my Chemistry 20 slide. I don't think you're getting assessed on this, but if you ever hear the term stock solution means like the really concentrate stuff. So this would be stock solution, because it's really concentrated, and this would be your diluted solution. When you make frozen orange juice, the frozen orange juice down the aisle is the stock. My wife makes soup with like concentrated chicken broth stock. You guys ever see that stuff? Yeah, right? Like, yeah, exactly, right? Yeah. And so that's like the really concentrated stuff. Don't drink that, that'd be disgusting. Did you? Is it gross? Oh, that'd be so disgusting. It's like drinking straight chicken noodle soup, only like
just take that package.
Too concentrate though.
Just like take the chicken package.
Okay, here's a visual of the same sort of thing here. Here you have a concentrated solution, and all you're doing is you're adding some water to it, and now it becomes less concentrated, right? Like that's just total common sense. So, here's another picture that kind of shows the concept. When we're in the chemistry lab, we're going to use often a tool here. Maybe I'll make you use one of these on our lab the other day. This is called a volumetric flask. Did I show you any of these in Chem 10 last year? All right. The way this volumetric flask works is that there's literally one line on it. That's it. And you have to basically add water right up until the bottom of the little curved section hits that line. And that's when you know that you've added exactly the right amount of water. I'll show you. measuring devices that we might use in the chemistry lab. So here's a graduated cylinder. It's reasonably good in terms of being a accurate measuring instrument. You see how this one right here, it also has markings on the side there, but they're more of like a rough measurement. It's more like, well, that's about 80, that's about 60, that's about 40. It's nowhere near like exact. That's the reason why. You guys see how the way this one works is that it gives a very, very large bulb towards the bottom, but then it's very skinny right here. When you add a little bit, it causes the solution to go up quite quickly there. So it means that you can be precise to literally the nearest drop when you use this one here, because if you add, like, say, 2 more drops, the volume goes up a considerable amount. Add 2 more drops, it keeps rising up. So this is a very precise measuring tool because you've got to measure the water exactly to this line. So it's kind of a unique measuring device because this one has a lot of different measurements on it. You could measure 10 or 20 or 30 on here. This one right here measures only one volume. It's only capable of measuring 100. But it's able to do that 100 very, very well, as opposed to this one here, which is like, it's about 80. You know what I'm saying? In the kitchen, you probably don't care. It's like, it's about 250 milliliters here, but it's about a cup, right? But in chemistry, you might want to be more exact. So that's why I have this slide in here, is just to show you the measuring tools we would use. So normally what you do is you pour in the concentrated stock solution first, and then you just add water until you finally get to that line, and then you just mix it up.
Inside the stock bottle.
Oh, right here?
Yeah.
Yeah, that's just a straw. Oh, yeah, I have some of those too somewhere. It is like a straw, like it's a spray bottle, so that you can like.
Okay. I thought it was like trying to pour it, but it's like a straw thing.
No, this is the bottom of the funnel right here, and then that's like a spray bottle kind of thing. Only it turns like a 90-degree turn, so that it doesn't just like. Otherwise, the liquid would both evaporate, and it might leak a little bit more. So by having it kind of turn a little bit there, it prevents those. Okay, let's try some examples here. So similar to how we've got our weak peroxide and our strong peroxide, although those are the wrong words, our dilute and our concentrate, I got the same thing here with some concentrated hydrochloric acid. Concentrated hydrochloric acid is 36%, which is like eat through the desk strong. And we want it to only be 10%. So the question is, well, how much of it do you need to make that? So here's your formula. This one's also not too bad. It's V1C1 equals V2C2. Or I's and F's. I don't really care what letters you use, but something along those lines. Over here, this is like the before values. This is your after values. So let's start with after. When you're done, you want to have a volume of 4 liters. And you only want it to be 10% strong. With me so far? Well, before you start, it actually comes 36%. Our question is, well, how much initial volume do we need? Now, do you need to have more than 4 liters or less than 4 liters? Way less, right? Because you're going to start with a little bit of the really concentrate stuff, add a whole bunch of water to it, and then when you're done, you'll have your 4 liters. So mathematically, how do you get the VI by itself? How do you get rid of the 36 here? Yeah, just divide it, yeah. Here's a really cool thing about this. When you divide both sides by 36%, the percent signs cancel. And it leaves you with liters as your final answer. So 4 times 10 divided by 36 means you need 1.1 liters. Okay, so start with 1.1 liters of the concentrate stuff. How much water do you need to add then? 2.9. You don't add 4 liters of water because you already started with 1.1 when you began, right? So take 1.1 liters of concentrate stuff, add 2.9 liters of water, you'll have now a total volume of 4 liters, and now it's not as strong. It's now diluted down. It's a pretty straightforward formula. Let me circle back to where I started class. My chemistry, it's 20 students. They struggle with this, though. I think the biggest reason they struggle with it is that they're not sure which scenario each one is. Because I've shown you guys like 5 or 6 or 7 different scenarios over the course of the day, and that's their struggle is when I show them how to solve it, they're like, oh, I can do that. But when they have to do it by themselves, they struggle because they don't know which of these formulas here to kind of work with sometimes. Does that make sense? So, let's do a couple more examples and we'll call it a day. A student is going to use 13.5 grams of calcium phosphate to make a solution in one of those 100 ml volumetric flasks. My question is, how concentrated is it? Now, if I ask you for the concentration, we can do this in multiple different ways. One of the ways we can do this is we can do it in moles per liter. Another way we can do it is in parts per million. And the third way we can do it is as a percentage. So there's actually multiple different ways of solving it. Let's do the last one first. The percentage one is actually the easiest one. As a percentage, we wouldn't be able to do volume divided by volume, but we could do what's known as a weight divided by volume. To find a weight divided by volume, I would take its weight and divide by its volume and times by 100. Which seems kind of silly because you're going to do 14.5 divided by 100 times by 100. So weight over volume kids often find to be the easiest. It's going to be 14.5%. Pretty straightforward. So 14.5% is, kind of a middle. If it was like 17% or 25%, then it's more concentrated. So far, so good? Okay, let's try the parts per million one. Parts per million, if you like using the one that's on here, that's fine. It's massive solute over massive solution. But if it doesn't give you both of them as a mass, you have to use milligrams per liter is the unit for it. So we actually have to convert both of these because neither of these are actually in the right unit. So I'm going to do them both in my head if you guys don't mind. To convert grams to milligrams, it's going to be 0.0145 milligrams because it's actually a smaller amount. No, it's not. That's wrong. All right, you have to times by 1,000 to get to milligrams. This would have been 14500 milligrams. That was wrong. And then that was in liters. So to convert milliliters to liters, you'd have to divide and make the 0.1 liters there. I kind of skipped the multiplying and dividing by 1,000 part. You guys able to handle that though? Okay. So 14500 divided by 0.1 gives you 145,000 parts per million. Which kind of makes sense because parts per million are usually used for things that are very, very trace amounts. And we dumped 14.5 grams in there. That's actually not a trace amount. That should be very large. I think this is, again, where kids get thrown off is because this was one option, this was another option, and then there's also a third option. I need you guys to be fluent in doing any of these ones. So for the last one, you need moles per liter. The problem is that I don't have moles, I have grams. So I would do this, 14.5 grams, and I'm going to multiply by a mole per gram. Try to cancel out the grams. This is what stumbles a lot of kids then. I got to find that molar gram sort of ratio, like we started class with. How do I find that? Where do we find the weight of all of our elements? Which is found on your periodic table. We got to add them together, but here's the problem. I need to know what calcium phosphate's formula is. And this is where if you really struggle with your grade 10 stuff, then it really comes back to bite you in the butt because if you need to know what a calcium phosphate is. So, I want to take a stab at it. What is a calcium phosphate's formula? Ca for calcium. What is a phosphate's formula? Say that loud. Yeah, you got it right. Good job. CaPO4. Now, is it one of each of them, or does the charges line up perfectly? Like, what's the charge for each?
Ca3 and PO4 2.
Yeah. Ca is a 2 plus, and PO4 is a 3 minus. So it means you're going to have 3 calciums and 2 phosphates. this is what throws a lot of the kids off then, is that if that's a struggle, then this becomes a struggle, and like the whole house of cards just tumbles. Okay, so we need 3 calciums. So calcium is, according to our data booklet, 40.08, and we need 3 of them. Phosphorus is 30.97. How many phosphorus do you need? 2. And then oxygen is 16 right on the dot. How many of those do you need? 8. The 4 and the 2, they times by each other. Alright, so add all that up. I got to 310.18. That's how many grams there are in a mole. So just to rehash again what a gram per mole is, that's how heavy one of that dozen of atoms would be. So this is actually a very heavy compound. Does that make sense? Like compared to the ones we did before, this is actually like really dense. This is like a walnut compared to a peanut in terms of like its heaviness. Does that work? So now that I have this number though, I can put it up here. Does it go with the mole number or the gram number though? Like where does the 310.18 number go, on the top or the bottom? It goes on the bottom. Good job, guys. Yeah. Because there's 310.18 grams in 1 mole. So I'm going to divide these two things by each other and give me 14.5 divided by 310.18. And it gives me 0.0467 moles. If you have a mole, it's going to weigh 300 grams. You only have 14 grams. Not even close to a mole. Does that make sense? 1 full dozen of these things would weigh 300 grams. You have 14 grams. You don't even have close to this dozen. Make sense? But we do know how many we have now. This is the number. To find the concentration, it's moles per liter. So we'll have to divide this number now by the liters value, which was 0.100 liters. Because you have to like divide this by 1,000. That'll get you your concentration. So divide by 0.1. Our concentration then is 0.467 capital M for moles per liter. 3 different ways of calculating concentration. One is moles per liter. Most kids, that's the hardest one for them. Parts per million, or weight, or some sort of percentage volume. Okay. I need for you guys to be able to do any of those 3. The struggle, like I said a little while ago, is probably just trying to figure out, well, which one are you doing, and how do I go about doing it? Because like they're all just a little bit different, right? Okay, I'm gonna stop there because I have a few more examples left, but maybe we'll do them tomorrow. So, how'd I do? That makes sense? We'll follow most of that. Okay, that's probably the easy part. The hard part is not doing it yourselves. So what I want to do tomorrow is I want to have you guys start working on that assignment to practice this concept. And then Thursday I want to do a lab to help give you some hands-on work on it. And then next week we'll do a quiz. We'll see where we're at. Okay. And if you tank the quiz, please don't freak out, because this freaks out my Chem 20 students. Like this is the hardest thing they do. So if you guys can handle this, that's absolutely fantastic. So. Okay. I guess we'll take off. I guess we'll talk to you tomorrow. We'll do those last 2 examples tomorrow, because there were 2 more left, right? Yeah. We'll just do those tomorrow to kind of do it, like to start our class. And I'll give you some work time. So. Okay.